Remember how arrays struggle with inserting at the beginning? Linked lists solve that.
Really? How?
A linked list is an ordered collection of elements. They're called nodes. Each node has two parts, data and next. Data stores the value. Next is a link, a reference to the following node. That's where the name linked list comes from. The data can be anything, characters, numbers, strings. In our case, the data are letters A, B, C, D, and E. We'll name each node after its data, node A, node B, and so on, just to keep things clear. Now, node A's next points to node B. Node B points to node C. See the pattern? Each node only knows one thing. Who's next? In node E, its next is null. That's how we know this is the end of the list. The list itself just holds one reference, the head. It points to the first node. If the list is empty, head is null. This setup, where each node points forward and we enter through the head, is also called a singly linked list. So how do we go through the list? We start at the head and follow the links. Let's say we want to print every value. Start at head, print A. Follow the link, print B. Then C, D, and E. But here's the thing. Unlike arrays, linked lists don't have indices. We can't just jump to any node we want. So even if we only need the last node, we have to walk through every node before it. There's no shortcut. Now, what about access speed? The head is always available. It's our entry point to the list. So accessing the first node is instant. Just one step. That's O of 1. But anything else? We have to traverse from the start. The deeper the node, the longer it takes. O of n. As we learned in the previous episode, arrays give you random access. Jump to any element instantly. Linked lists, as we just saw, sequential only. One step at a time. That's their biggest weakness. But don't give up on them yet. Let's look at what linked lists do better.
Wait, so linked lists are slower? Why would anyone use them then?
Because linked lists are great at something arrays struggle with, insertion and deletion at the beginning. Let's see how to add a new node. We'll start with insertion at the beginning. First, we create a new node. Let's call it node A. Since head gives us a reference to the first node, we can set our new node's next link to point to it. Finally, we update head to point to our new node. Done. The new node is now first in the list. No shifting, no moving other elements. Just two simple steps. That's O of 1, constant time. But we don't always insert at the beginning. Sometimes we need to add a node somewhere in the middle. Let's see how that works. Say we want to insert a new node right after node B. To insert after node B, we first need to find it. We use a marker called pred, short for predecessor, because this node will come right before our new one. It starts at the head. We move the marker through the list until we reach node B. Now we have access to it and can insert our new node right after. Once we're there, we create our new node, node C. We set its next link to point where node B was pointing. That's node D. Then we update node B's next to point to node C. And we're done. C is now between B and D. What about adding to the end? Same idea. We walk through the list until we find the last node. That's the one whose next is null. Node D is found. Its next is null, so this is the end of a list. We create our new node, node E. In the last step, we set node D's next link to point to node E. Done. Our new node is now at the end of a list.
So for deletion, it's the same, just one marker?
Not quite. Deletion is a bit different. We'll start from the end, removing the last node. This time we need two markers. In code, these are just variables. The markers here are simply how we visualize them. Pred, our predecessor, like before, and temp, short for temporary, which marks the node we're about to delete. We move both markers through the list. Temp stays one step ahead of pred, always pointing to the next node. We stop when temp reaches a node whose next is null. That's the last node, the one we want to delete. Now we set pred's next link to null. This removes the connection to node E. And just like that, node E is no longer part of the list. The memory it used will be freed up, either automatically or manually, depending on the language. Now let's remove a node from the middle. Say we want to delete node C. Same approach. We use pred and temp. We move them through the list until temp points to node C, the one we want to delete. The node we want to delete is found, and having a reference to the node before it, that's what makes the deletion possible. We take node B and redirect its link, skipping over node C, pointing straight to what comes after it. Nothing points to node C anymore. It's isolated. And when a node has no incoming links, it's considered removed from the list. And the last case, deletion at the beginning. This one is different. We don't need to traverse anything. We simply move the head pointer forward to the second node. That's the only thing we need to do. The first node has no references left. Nothing points to it, so it's gone in a single step. Now that we covered insertion and deletion, let's see the full picture. We've seen how arrays behave. Now let's fill in the linked list side. At the beginning, constant time, we have direct access to the first node, and all we do is update one link. In the middle, linear time, we have to walk through the list first to find the right position. That traversal is what costs us. Same for the end. No direct access to the last node. We have to get there step by step. Arrays are faster at the end. They can jump straight to the last position, no traversal needed. Though there's a small nuance here depending on the type of array, but that's a topic for another time. But linked lists win at the beginning. For arrays, adding or removing at the start means shifting every element. Here, it's just one step. So the pattern is clear. Linked lists are fast where arrays are slow at the beginning, and arrays are fast where linked lists are slow at the end. In the middle, both are linear, but for different reasons. Arrays have to shift elements. Linked lists have to traverse to find a position. If you've made it this far, nice work. To see all of this in action, check out the VisiGrab app. The link is in the description.
Do I really have to hold those sausages?
Yes.
Fine.